Okay, so let me first go over something that I skipped last time because I wanted to go through the Massless case. Let's jump to the general case, but only for a just looking at the Wigner rotations. So let's imagine that we're considering remember the general Wigner rotation is L inverse of lambda p, lambda L of p, and in general, for massive particles, this is a rotation, and for massless particles, we'll basically force it to be a rotation. In any event, it's a member of the little group, and always when W of lambda and P takes K into K, whatever K happens to be. For massive particles, K is M0, 0, 0. For massless particles, I took K to be 1, 1, 0, 0. Weinberg chooses it to be 1, 0, 0, 1, and that's because he puts the 0 down in 4 positions so that it's next to the 3. Or to put it differently, he writes things 1, 2, 3, 4 in order to get Z next to 0, which he calls 4. Okay, the important thing is that if lambda is actually a rotation, then W itself is a rotation. In fact, it's the same rotation. So let's just write this for some rotation R prime P. So this is L inverse of R prime and P, R prime L of P. And for the case of massless particles, L of P is some standard R, a standard L of P, and then an R inverse. And this standard L of P is such that L of P takes K into P. That's not a unique choice, so that's why I call it the standard L of P. And R inverse, of course, has no effect on P for a massive particle. And in fact, for massless particles, L of P, well, L of P always takes K into P, but for massless particles, L of P is simply R times a boost that takes the fiducial vector. In Weinberg's case, it's in momentum 1 in the z direction. It takes it into momentum p in the z direction. If one instead uses this fiducial vector, then the boost would be in the 1 direction. Okay, so I've gone off on a couple of tangents from my notes, so let me get back to what we have here. So this W of R prime and P is L inverse of R prime and P R prime, and then this L of P for a massive particle is R L of P, R inverse. Now let's figure out what this is. Again, we're talking about a massless particle. And here, in fact, let me erase the massless case because we're not talking about the massless case yet. So this R here takes the vector in the z hat direction into a vector in the p hat direction. That's what R does. And so what is L of R prime of P? Well, it's just from this general rule, it's R of R prime and P, B of P, R of R prime and P inverse, following this rule here, where I left out the fact that there's a P here. Now, what is this R of R prime of P? Well, R of R prime and P takes Z hat into R prime of P hat. Or equivalently, it takes it into R prime R of Z hat. So in other words, R of R prime and P is R prime R. And if you want, it's R prime R of P. Yes?
So what does it mean when you're putting R prime and P inside like a function of big R? I kind of lost there.
Well, L is a function of a form momentum.
Yeah, okay.
This is the rotated form momentum.
Okay.
Arbitrary rotation.
Okay.
I don't have any more candy, so I can't toss you a candy.
But what does it mean when it's in the big
I
R?
promised to buy some over the weekend.
Okay.
All right.
So I think he had another question here.
Yeah, what does it mean when it's in the big R? You told me what it meant when it was in the L, but you have this like big R and then you have this R prime P in parentheses, like right next to what you were just explaining. It's equal to what you were. So go over a little bit. Over more. There, that big R, and that has stuff in it.
That's R of R prime P, and what does that do? R of R prime P takes the Z hat vector into the rotated P hat.
Okay.
Yeah, I was wondering why. So why do we have this property that R of P, L of P, R of P inverse equals R of P?
You mean this one here?
Yeah. Why? Is
This.
That? Yeah. Why?
This is the definition. This is the definition of the standard Lorentz transformation for massive particles. Now, it's not. In other words, it's not one of the 10 Commandments.
Okay. So
it's Weinberg's choice of a standard Lorentz transformation, and there's a technical reason why you have this R inverse in the front. I've forgotten what it is, but I once knew.
So does this also come? So does this come from this other definition that we have for L of P? Because I thought that this was
Did what come from
what
it? This?
L of P is. Yeah, this relation.
No, this is this choice of a standard L of P. First of all, it's an arbitrary choice, but it's a wise choice for various reasons. First, so you could do physics with a different definition. In particular, you could drop this term entirely because in the massive case it doesn't make any difference. Okay, R inverse doesn't have any effect on M0.
Yeah, sure.
But for technical reasons, it's a good idea. Now, there's still something that's. This is actually incorrect because I wasn't looking at my notes. This is not L of P. This is B of P. Okay, that must be what confused you and why you guys asked these questions. So let me then repeat. The standard Lorentz transformation is an R for mass of particles is an R inverse of P, a boost that takes M0 into P hat. So B of P on Z hat is I don't know, well, it boosts, actually it boosts K into P. P in the Z direction. Okay, it's a boost in the Z direction.
So it's the magnitude of P, but times like Z hat or something?
Yeah, but the trouble is that it's not magnitude of P because there's P0 and P vector, and they're not the same length.
Well, Professor.
So that's what this, so the standard Lorentz, so the standard Lorentz transformation has a technical factor in the front that has no effect on K. Then it takes K into P, but pointing in the Z direction. Then it rotates P from the Z direction into the P direction. So finally, L of P on K is P.
Professor, about the V of P f of K gives us PZ, can you write it? I'm very confused about this part. Can you write it in the form of matrix?
What the boost is? Well, the boost, actually the boost is I wrote it last time in Weinberg's notation where, let me see if I can switch to a better notation instantaneously. Okay, B of, he writes it as length of P. And I think this is the right way to write it. I think that's right. So that takes, so B of P takes K, which is to say M000 into gamma M 0, 0, square root of gamma squared minus 1 M. And this satisfies the relation gamma squared m squared minus gamma squared minus 1 m squared is equal to m squared, which is to say p0 squared minus p vector squared is equal to m squared. In Weinberg's book, unfortunately, he throws the gamma, he throws 0 into 4, which...
I do have a question, but I thought you were still finishing that.
You have a question?
On your last, your L of R prime P, why does the boost not have a rotation in it? On the right-hand side?
The boost is always dependent only on the absolute value of the momentum, not the direction. It's a standard boost in the Z direction.
Okay.
These are great questions. I'm amazed that I'm getting more questions without canding than with canding. Maybe it's that fumbling for the candy and throwing it to the student slows the class down in a way that irritates everybody. I don't know.
We're afraid of getting hit by the candy.
Huh?
We're afraid of getting hit by the candy.
Yeah.
Wait, and so then another question. What is R prime do again? I forgot what R prime does. Like what's the difference between R and
R of R prime P takes Z hat into R prime P hat.
So it's just another.
So it's a rotation. You see, P has a certain direction. Then, when R prime acts on P, you get a different direction.
Okay.
And so R of R prime P is something that takes Z hat into R prime P. And another thing that takes Z hat into R prime P is R prime, the rotation times the standard rotation times Z hat.
Sure.
And so one gets from that R of R prime P is R prime R.
Okay. But yeah, so what's the significance of it?
All right,
I
well,
mean, it seems
well,
like
let
you're
me
just
give me a break. I've got to get to the
yeah.
next stage, if I can even find where I am here in the notes here. Okay, well, what this tells us then is that L of R prime P is R prime R, B of P, R inverse, R prime inverse. And consequently, L inverse of R prime P is R prime R, B inverse of P, R inverse R prime inverse. So now, W of R prime and P is this thing, which is R prime R, B inverse, R inverse, R prime inverse, R prime, R, B, R inverse. Now, what is this? This is L of P. This is, of course, R prime, and this is L inverse of R prime of P. So I'm just writing these in parentheses. That's what W is. But now what we see is a cascade of cancellations, because this is first, these two guys cancel, and we get R prime R, B inverse, R inverse. This just gives the identity. Then we have RB, R inverse. Now these two cancel, and so we get R prime R, B inverse B, R inverse. The B's cancel, and we get R prime R, R inverse. And now this finally gives us R prime. So what this tells us is that the Wigner rotation corresponding to an arbitrary formal method and a Lorentz transformation that actually is a rotation, that Wigner rotation is that rotation, R prime. It's appropriate that you're raising your hand because I'm about to answer the question you asked me in class, in my office yesterday. I think it'll do everybody some good to go through it. But what's your present question?
Oh, so where here did we kind of enforce that we were working with a massless particle? Was that when we defined?
Well, here we're today. I'm here.
Massive.
I'm just
Sorry,
talking about
massive.
massive.
Sorry, I meant massive. Because we just showed.
Why is it that we're talking about massive ones?
No, like where did we like enforce that we are? Because we've just shown that the Wigner group reduces to a rotation, and that's
For massive
that's
particles.
only true for massive.
For massive
Yeah,
particles.
that's only true for massive particles. So where did we kind of like put in the fact that we were working with massive particles versus?
Well, the whole bloody thing, the choice, first of all, the choice of L being of this form, this wouldn't work if it were massless. And in fact, for massless particles, L0 of P is just R B of P. So it's just a boost in the z direction followed by a rotation. So this extra factor in the front is omitted. And because it's not physically necessary, it's necessary for technical reasons.
And if you have that when you're trying to do this for massless particle, it doesn't work.
No, I'm not doing it for massless particles.
No, but it doesn't work if you try to. That's what I'm asking.
Well, the other thing is that, remember, when we talked about the Wigner group, the little group last time, and looked at the case of massless particles, what we found was that it was basically a combination. The way I did it in class, it was I had K being in the one direction, and the Wigner, the element of the little group, was a rotation about the one direction. And then there were two other possible things, but they were combinations of rotations about the two direction and a boost in the three direction, or a rotation about the three direction and a boost in the two direction. And what actually, well, in any case, those things aren't rotations, okay? They've got Lorentz boosts in them. So it's quite different. And in fact, it's actually mysterious. What Weinberg will eventually say here, he says that it's related to gauge invariance, and moreover, it's also related to the fact that, in a sense, the electromagnetic field isn't a field like other fields, and also the graviton field isn't a field like massive fields. And this difference raises another question, though, because in the present view of field theory, the idea is that all the particles, without interaction, if you said all the coupling constants equal to 0, all the particles are massless because they get their masses from the Higgs boson. And so then we would have this issue with mass, this massless issue with all the fields. Well, it turns out that for spin 0 and spin 1/2, this doesn't cause a problem. Anyway, there are some subtleties here that I think we'll just say we'll just leave them as open questions. Let me now go to the question you asked, which confused me yesterday with class. And it has to do with rotation. This is, in a sense, it's a very simple question, but one can get confused. So let's consider translations. And what about representations of the group of translations? Of course, the group of translations is an abelian group. You have T of A followed by T of B gives us T of B plus A or A plus B, however you want to think about it. So this is on the group level, or the physical level. these are represented then by unitary operators, e to the minus I p dot b, I'm setting h bar equal to 1. E times e to the minus I p dot a, and this is e to the minus I p dot b plus b. And a and b here are, you should think of them as 3 vectors because we're talking about, well, actually they can be 4 vectors. So let's call them 4 vectors, and I'll get rid of the arrows. Typical, and so I don't want, well, whether it's a dot product or not depends on what one means by a dot product. So, and in fact, what this actually does mean, p dot a here is really p vector dot a vector minus, in fact, these are momentum operators, so this is minus the Hamiltonian times the time, say. Again, c equals 1. Well, TCA. Or A0. Equivalently, p dot a minus p0 h. Okay, anyway, the point is these are unitary operators. And they act on states, so e to the minus I p dot b on a state, say, x is x plus b. And if you act on both of them, then what you have is e to the minus I p a plus b on, say, x is x plus a plus b. This is linear and unitary in the sense that e to the minus I p dot a on, say, alpha x plus beta y is alpha x plus a beta y plus a. Okay. So this is what we mean by representations of, in particular, this simple group of translations. This, of course, is an Abelian group. The reason why I'm bringing this up is that, what is your name? I'm terrible with names.
We were together for a whole semester. Sam.
I have trouble remembering my son's 3 names because there are 3 of them. Huh?
Sam.
Sam.
Yeah.
That's right. Sam. Yeah. Now I remember. Well, what Sam? Sam got me completely confused yesterday because he was saying, well, what was he saying exactly? You were right. You were moving some point x to x plus a, and then you were moving y to y plus a, but then you were asking, well, what about x plus y? Well, this goes to x plus y plus 2a. Okay. So you must keep in mind that this is not what we mean by the representations of the translations. Okay. In other words, if we're acting on 2 states, each state moves. That's the sense in which it's linear and unitary. Not this sense. This is something else.
Can you write a finite dimensional representation of a translation?
No, there is no finite dimensional representation of the translations which are non-compact. And this puzzle, your puzzle and this may be related to the absence of finite dimensional representation. I'm not sure. Okay, let me just see what All right, let me go back to the massless case now, just very briefly. We last time had the B2 minus R3 on my K vector was B3 plus R2 on K, and both of these was 0. This is where K is 0, 1, 1, 0, 0. Weinberg does it a little bit differently, but let's stay with this just for a second. Remember the J's, Ji is I, Ri, Ki is I, Bi, and now let's see. These Ri's are real and antisymmetric, so this thing, so as a 4x4 matrix, these J's are Hermitian.
So this K is different from the usual state K, right? Completely
Right, this
different?
is lowercase k.
Okay.
Good point. Now, the B's are symmetric and real, so they're Hermitian. The K's are anti-Hermitian. On the other hand, so this is at the matrix level. On the other hand, when we promote these two operators, the J's are represented as Hermitian operators, and the K's become Hermitian operators, even though they're represented by anti-Hermitian matrices. So this is where you go from infinite dimensional unitary to finite dimensional non-unitary. So what we have here is that W has to be something like e to the I alpha. Okay, now I'm switching to Weinberg's notation, where Weinberg uses K 1001, and his things, instead of being, mine were K2 and K3. He has and J1. He has J3 and then K1 and K2 and J1 and J2. And so, for his case, what you have is so this is what the Wigner operator is. But on the other hand, because of the K's here, there are no finite dimensional representations. And so what Weinberg does is say that K1 plus J2 simply annihilates the massless state K, and that K2 minus J1 also annihilates the state K for the massless case. And so let's just go with that for the moment. Then what E has for massless particles is U of lambda on the state P sigma, square root of lambda P0 over P0, simply E to the I sigma times the theta of lambda in P, lambda P sigma, where the theta is, once again, though, his L of P is R of P hat, B of P, and his K, again, is 1, 0, 0, 1. B is a boost in the 3 direction. In fact, in massive and massless case, it's always a boost in the 3 direction. And and his U of R is either minus I phi J3 e to the minus I theta J2. In the first printing of his book, there were plus signs here. They're actually minus signs. Your version will be minus. All right, so let's now skip ahead. And in fact, I want to skip the rest of the stuff in chapter 2. I want to skip chapter 3 completely. If you want to, if it wouldn't hurt anyone to read chapter 3, but there's a lot of technical material that's not totally necessary. I think it's of secondary importance. And so let's just skip that and go directly to states of many particles. Well, what are they? Well, it's P1, sigma 1, N1, dot, 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 Pn, sigma n. Well, n sub n. Or let us call it m. N sub n. P is momentum, and in fact, Weinberg normally imagines this, it takes the trouble to distinguish between whether he's talking 3 momentum or 4 momentum. The difference is kind of academic though. Sigma is the spin in the z direction for massive particles, and it's the helicity for massless particles. Helicity being the amount of angular momentum in the direction of motion divided by the momentum, and so it's effectively plus or minus 1 for photons, plus or minus 2 gravitons. And N is just the type of particle, so E for electron, QR for red quark, and QRU for headed up quark. But in fact, what we're going to do pretty soon is we're just going to let Q stand for P sigma and whatever that is. And so this goes down to Qn. I'm going to switch back to N. Okay, well, here's the key thing that's really remarkable and of enormous importance. If you have a multi-particle state described this way, n particles of different kinds, this is always equal, it has to be equal to a phase factor times the same state, but with Qk and Qi interchanged. Oh God, that bug is so big to write it. Okay, anyway.
I think there's a requirement that you can't call them roaches at that point.
Anyway, so let's see. Both represent the same state, and remember, as Weinberg points out rather carefully, oh God, he slipped on the chalk and he's upside down. Somebody have a piece of paper? Here, give me your paper. Let me flip this guy up. It's terrible.
It's my homework, Kevin.
There he goes. All right.
That's my homework, you can keep it.
Huh?
It's my homework, you can keep it.
Well, I want to turn it into.
This is leave a note on the top. This has roaches.
Actually, roaches are very clean. They're always cleaning themselves. How, I don't know. But apparently, I've been told by very good experimentalists that roaches are very good. I get a fondness for roaches. Anyway, what you can see, though, is if you re-interchange QI and QK, then you're going to get either the 2I theta, Q1, QI, QK, Qn, and so one gets a conclusion that either the 2I theta is equal to 1. Now that's if this angle is purely related to the order of the states. And Weinberg goes through a discussion of this, which, if I were doing class, I would basically have to read the discussion to you. And so I think I'm going to let you read it if you want. On the other hand, you could also skip it because it's of interest. It's of interest. In particular, he points out that if we were in two space and one time dimension, then this angle could depend not simply on the order, but on the way in which the particles were brought to their positions. And so in particular, there might be some point here, and the particle 1 could be brought from, say, infinity to this point, and then, but another possibility is going around twice and going to that point with particle 2 and so forth. So the state could reflect the history, and if the state reflects the history, then there could be an extra phase. And this is something that Wilczek ran with, and he invented particles that do this, particles that have statistics that are not Fermi-Dirac, I'm sorry, that are not Dirac, that aren't bosons or fermions. He called them anyons, and they can occur in field theories of two space and one time dimension. I imagine that solid state or condensed matter physicists have found physical systems that exhibit anyon properties, but I actually don't remember if that's the case or not. Anyway, you can Google it and find out. So, to recapitulate, in three space and one time, which is where we are apparently, but not necessarily, if the angle only depends upon the order, then it really is true that either 2I theta is 1. And that's the general, so that's what we're going to assume.
I have a question on that. So you said in three space and one time, that's true.
Yeah.
I don't see
That's
any reason
That's
why.
where we live, yes.
But is it restricted to those dimensions, or if it's 12 space and one time?
Is it what?
Said even if it was 12 spaces in one time. then
Oh,
should
I
it
don't
still
know. That's interesting. 12 space and one time. I imagine that you still get this. I think you need a two-dimensional space, but I'm not sure. It's a mathematical argument that I haven't looked at recently. You can Google anyons, the PRL of Wilczek 20 years ago or something like that. Wilczek has a good sense of language when he names things. He also named the axions, but he claims that he named the axion after a laundry detergent called axion. Yeah.
I disagree that that's a good choice of name, because it sounds too much like anion.
Like what?
Like anion.
Oh, yeah.
So I think if you cause confusion.
No, you're right, but, you know, this isn't a chemistry class, so, but you're right. In fact, I don't even know how to pronounce anions. Anions or anions? All right, anyway. let's get back to the real world of field theory. So, how are we going to define a creation operator? Well, a creation operator of kind Q on a state with already particles Q1 through Qn that represents already these particles is simply going to be Q, Q1, Q2, Qn. So the idea is that it adds the Q to the first position. And here, once again, Q is momentum, velocity, well, momentum, the spin label, and the kind label. And in particular, then, you can imagine that all the states arise from the vacuum state. The single particle state Q is a dagger Q, a dagger of Q acting on the vacuum state. Vacuum state is normalized, and the idea is that you make all the states from the vacuum state, and one normally assumes the vacuum state's unique. It's the state of lowest energy and so forth. And of course, what's a big mystery these days is that it's plausible that dark energy is simply the energy density of the vacuum state, the state of lowest energy in whatever's the true quantum field theory, which itself could be a limit of some string theory or M theory or whatever, or something better. Yeah.
So, are all these Qs the same particles that they're identical?
Give me that again.
Are all these Qs identical particles?
No.
Because I thought you only got this exchange.
Right.
This
N can
Yeah.
be, electron. This one could be neutrino. Could be anything.
So, but if you exchange two non-identical particles, you could tell the states apart, which means they would have to differ by more than just a number of states.
But exchange means that you just exchange the order you've written them.
Okay.
They're the same. They have the same momentum and
Oh,
velocity.
so you have an exchange
Or
of
if we
space.
were in a particle position representation instead of a momentum representation, then we would say that this is, the particle of type QK is at one position, but the position isn't the position here. It's a certain position, and particle QI is at another position. But this state over here represents the particles at the same places, just the order of writing them is different. And so the order in which the creation operators occur. So in other words, it would be this thing here, in other words, is equal to a dagger Q1. God, no eraser. Let me get that. Oh, here it is. Let me just do ... A dagger of QI, ... a dagger of QK, ... a dagger of QN on vacuum. Okay? That's this state. On the other hand, what we're saying is that this is EVI theta, and then a dagger of Q1, ... a dagger of QK, ... a dagger QI, a dagger QN vacuum. So the idea is that the order of the creation operators is different.
So it's not like you're switching two particles in space. It's like you're creating.
We're not exchanging their positions in physical space or momentum space, right? We're just interchanging their positions in our mathematical conceptual space, the way we represent things. Weinberg goes on to show, and so this is sort of obvious, Well, I'm not sure what the order of this is. Let me just write down what, since I'm skipping over the proofs of all these things. First of all, if there are different numbers of particles, the states are orthogonal. And then we sum over all permutations. Product I equals 1 to, I guess, minimum of N and M. Delta Qi minus Q of Pi. And, oh, yeah, where delta, his delta of Q is, so Q1 minus Q2 is delta of the 3 momentum Q1 minus 3 momentum Q2, delta sigma 1, sigma 2, delta type 1, type 2. And so in other words, these states, I mean, it might be electron neutrino here, it might be neutrino electron here for two-particle state. But if they have the same momenta, then you get something around 0 here when you permute 1 and 2. In any event, these are for bosons, one then has A of Q, a dagger of Q prime is delta of Q minus Q prime. For fermion, ordinary commutator, for fermions, one has the anti-commutator, which is a dagger, A of Q, a dagger of Q prime plus a dagger of Q prime, A of Q, equals delta of Q minus Q prime. So in other words, the fermion, all the fermion operators ain't like Q. All the boson operators have a commutator that's proportional to the delta function.
How do we know that they're boson fermion? Is that just implied by the Q? Whether they can be?
Yeah. There'll be an N there.
Okay.
Q is P sigma N. So N will say, electron, so you know it's a fermion. Now, what we're going to be assuming here is that the unitary operator that represents a Lorentz transformation and a translation acting on the vacuum is the vacuum. Weinberg actually goes to the trouble of distinguishing between the Lorentz transformation and the one that's appropriate for free particles and fields. And his thinking there is that if the particles are free and we set all the interactions to 0, we know what we're doing, and we can think in terms of perturbation theory, and we more or less know what we're doing, and so we can make these statements and even prove them. But if one is talking about fully interacting quantum field theory, then it's just hopelessly complicated, and we have no idea what's actually happening. Yeah.
So what's this U0?
U0 just means we're talking about free fields.
Free field.
And we're setting all the interactions to 0.
Okay. And then Lorentz, it's a representation of Lorentz transformation.
And a translation. And when you combine the Lorentz with the translation, this is called the Poincare group.
Okay. So A is a translation here, not an annihilation equation.
Yes, right. Absolutely. Good point. I once got a bad grade in an algebra test, abstract algebra test when I was in college, and I was a sophomore. Because I proved something correctly, but I used the letter A for 3 different totally unrelated formulas. I tried to get the professor to give me credit anyway, but he was Scotch and he wouldn't. It was actually a terrible lecture. This is where you would lecture. You have an eraser in the left hand, talk with a Scottish accent, write with the right hand, you go like this. So you had to catch what he wrote after the chalk right, was there, before the shoulder, after the shoulder, before the eraser. It was really tricky. Okay, now, how do these, we've taken the trouble the last couple of weeks to say something about how states transform under Lorentz transformations, and translations for that matter. And so that tells us how states transform, how creation operators have to transform. And in particular, this is a Lorentz transformation. In fact, he uses alpha here. And the reason he did was to avoid the question you just asked. So a dagger, now let's do P sigma n. So this is, so we can infer then how a creation operator transforms, since we know how states transform. And in particular, for massive particles, we have there are no more subtleties. And so we can just say this is e to the minus I lambda p dot alpha square root of lambda p 0 over p 0 some sigma prime the jth representation, the Wigner rotation, massive particles again, and then a dagger of lambda p sigma prime n. Okay, so what Weinberg has, I skipped the statement here. So this, what is actually happening? What's actually happening in this U0 of lambda and alpha is that we have e to the minus I p dot a, and then the Lorentz transformation, and I'll just write it as U0 of lambda. So first we do the Lorentz transformation. The operator then describes something of momentum of lambda p, and so when the translation hits, what gets translated is the phase factor as lambda p dot alpha, not p dot alpha. So it's, if you did it the other way about, put the momentum here and the U0 there, this would be a simpler expression. It would just have p instead of lambda. So that's not a big deal one way or the other. Okay. Let me now get back to something that I'm also skipping chapter 4. Chapter 4, among other things, is a deep discussion of what Weinberg calls cluster decomposition, and basically what guarantees that if you do an experiment, you do two experiments that are way far apart in space-time, they shouldn't have any effect one on the other. So experiments done in New York should screw up experiments done in San Francisco. Now, of course, if you're talking about creating a neutrino beam in New York and detecting it in San Francisco, that's another matter. But such things aside, one avoids this crazy sci-fi business of experiment of physical processes interfering with each other when they have no business to be related to each other. In part by having by describing things in terms of creation and annihilation operators, and there's also the following. That any operator in this theory can be written as a sum of things like, well, let me just write, let me not write in terms of sum, actually, but it can be written as some constant plus another constant times AIs plus another constant AI daggers plus another other constants, AI dagger, AJ, plus another constant, AI dagger, AJ dagger, AK, plus, and so forth, until finally you have something that's AI dagger, AJ dagger, AK dagger, A alpha, A beta, A gamma, In other words, you can, by using the commutation or anti-commutation relations, you can rewrite any operator in what's called normally ordered form. And this is convenient for a number of reasons. In particular, if you take the mean value in the vacuum of any such operator, what you get is just C, because all the other terms vanish because they're normally ordered. And in particular, the annihilation operator, in fact, this was an equation that was in my notes, but I forgot to write down. I skipped it because it looked so innocent. Right. The annihilation operator, let me just call it A of Q. On a state Q1, Qn. This is actually a sum plus or minus to the R plus 1, R equals 1 to n, delta of Q minus QR, and then the state Q1, no QR, Qn. So what the annihilation operator does is it subtracts the state. Let's see. It looks in this thing. If any of the Q's match Q, it takes it out and leaves the others. If it can't find anything that matches it, it just maps the state to 0. So in other words, to imagine we're just dealing with scalar particles then. A of P on a state P prime is just delta of P minus P prime. And A of P on a state that might be, say, Q not equal to P will then be plus or minus Q. In other words, we'll take out the state P, and if A annihilates a fermion, and if Q is a fermion, then we'll get a minus sign, otherwise we get a plus sign. Okay? right, now, as I said, in chapter 3, Weinberg talks about the S matrix, and the S matrix is basically what describes scattering. In other words, you have some incoming state, P1, Pn, and the amplitude for getting, say, P prime 1, P prime n, dot, 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 with possibly other particles, or pure particles. This amplitude is called the S matrix. And let me just call it P prime P, maybe a semicolon. Now, since this describes scattering of physical particles, we want this to respect special relativity, and so it should be Lorentz invariant. And what Weinberg shows is that it can be Lorentz invariant if the interaction is an integral over space of a Hamiltonian density that transforms properly. The transforms as a scalar. In other words, U0 of lambda and A, H of X, U0 inverse of lambda and A is just H of lambda X plus A. And by the way, the reason that now that I think about it is why Weinberg chooses to put the translation operator second after the Lorentz transformation is that then you get a nice simple form here. Otherwise, you would have lambda A, you would have a lambda on the A, even more complicated. You have a question?
Yeah, what does this like O represent? I missed that.
Oh, this is just any operator.
Any operator. It can be written in terms of creation and annihilation operators. So like
Yeah,
you can express
any
the
operator,
observable.
it not simply can be written in terms of them, but by using the commutation or anti-commutation relations, you can normally order the things. So you can pull the creation operators to the left.
So you can write like observables like this.
So in other words, the standard thing that you learn on day one in a quantum optics class is that A prime dagger is A prime dagger A plus delta of P minus P prime. I guess it's actually that term.
I was going to ask, were you saying something like this normally ordering has something to do with what you were saying at the beginning about experiments that are done very far apart from each other, not affecting one another? Or am I just mishearing what you said?
What I was saying was that what Weinberg shows in chapters 3 and 4, and to some extent in 5, is that if you formulate physics in terms of fields constructed from creation and annihilation operators that behave this way, then you have you can have an S matrix that's Lorentz invariant and has this cluster decomposition property, namely that far off experiments don't screw each other up, don't interfere with each other in some absurd ways. And so that's an important thing, but it's something that's left out in virtually all other books on quantum field theory. It's just something nice to know about, but I mean, there's a lot of, as I said to you before, Weinberg is very smart, and he can construct proofs that are very complicated for things that are subtle, and we would use up an awful lot of neural activity mastering all these details, and they're not at the moment essential for physics. In other words, I'm not sure what's going to change in physics in the next 20 years, but I don't think the things we're skipping over are going to be the key features that will prompt discoveries. But it's good that he does what he's doing, because then we can all relax and say, all right, he did it, we don't have to screw around. By the way, one thing I am sure is going to change a lot in the next 10 years, let alone 20, is we're going to know an awful lot more about astronomy because of gravitational waves. And the limit, I think I quoted the limit of the mass of the graviton incorrectly by 10 orders of magnitude. It's actually that mg is less than 2 times 10 to the minus 25 electron volts. And by the way, the Hubble constant, or to put it differently, h times the Hubble constant is roughly 10 to the minus 33 electron volts. So we're not that far away from something that's purely a cosmological wavelength. And other things that have been discovered are these observations of frame dragging and so forth. It's all quite remarkable. Okay, let me go on with, right, the other thing one wants is not simply that the Hamiltonian density transform like a scalar, but we also want h of x to commute with h of x prime if x minus x prime squared is greater than 0. In other words, for space-like separations, the two Hamiltonians should commute with each other. And that's true whether it's a fermion theory or a Boson theory. Now, as I said, fields do this, so let me, in the last 3 minutes, just say what we mean by fields, and then we'll pick this up next time, which I guess is next Tuesday. And this is some detail, again, where Weinberg goes into the details, but I think these details are worth going through. So I'm going to do some of this in detail in class. So here, psi L plus, this is plus means in the lingo of the 1940s, which I never learned, this is called the positive frequency part of the field. So this is then the sum on sigma integral dqp UL of x, p and sigma, A of p, sigma, and type n. So this is field of type n here. And then the negative frequency part is the same thing, more or less, but now we're going to be doing it for the antiparticles, so it's BL of x, p sigma, A dagger, p sigma, n, and now that I mentioned antiparticles, that should be an n bar. Let me make sure there's an n bar there. No, he doesn't make it an n bar. All right, so he's not, that's funny. All right, well, he's just saying it's the creation operator corresponding to the annihilation operator, A, P sigma, N. All right, so what we're going to want then is that U0 of lambda and A, psi plus or minus of L of X, U0 inverse of lambda and A. And in fact, I think he calls that alpha. I call that alpha. this is going to be a sum on L prime, dL prime, J, lambda inverse, psi plus or minus L prime, lambda x plus A. So in other words, we can have a Lorentz invariant field theory that respects cluster decomposition if, that's funny, where's the space back? Oh, it was in the field. Okay, so basically we want the positive and negative frequency parts of the field under a Poincare transformation transformed this way. What's this? This is the finite dimensional non-unitary, so finite dimensional non-unitary rep of the Lorentz group, and I'll say more about it next time, actually. Remember that I said that when you take these operators J plus or minus IK, I think that was the way to do it, and we call these J plus or minus, and maybe there's a root 2, I don't remember, or 1/2. These guys have commutation relations that are just, what you have is J plus I, J plus J, I epsilon IJK, J plus K, and the same thing for minus, with a minus there, and J plus with J minus, always 0. So that means that the J pluses have the Lie algebra of the rotation group, the J minuses have the Lie algebra of the rotation group. So you can have a finite dimensional representation of the J of e to the I J plus as a finite dimensional representation, and it's because you have the Lie algebra of the rotation group, you then have you have matrices that are just built from the matrices, the finite dimensional matrices that represent rotations. And maybe I'll just mention that, I'll just show you that in a little more detail in class next time. I already did it, I think, the week before last, but I'll do it again. And then also I want to go through a little argument about the connection between spin and statistics that I think is nice, and that maybe one of you can figure out how to improve. It's not a proof of the spin statistics theorem, but it's a very simple argument that shows you that one has a lot to do with the other. That is to say, the properties of fields under rotations are clearly related to whether the field's commute or anti-commute at space-like separations. The problem is it's not quite a proof, and I don't know how to make it a proof. But one of you guys can improve it, so much the better. All right, I'm over time already, so let's just turn the thing off. Unless there's another question? No, okay.